Everyone, so some of you had requested this problem. For those of you that were in my 5th period physics, we did this today as part of our competition. If you're watching this as the 6th period physics, we haven't done this in class, but you can still watch the video and figure out how to do this type of problem. So we have a projectile that's being launched off a 23.0 meter cliff with an initial velocity of 15 meters per second at an angle of 20.0 degrees with respect to the horizontal. Find how far the projectile landed from the base of the cliff. So the very first thing that you want to do is to draw a diagram and write down what you know. And it could be either given to you or things that you have to assume. So in this, I have a cliff. So draw a cliff. And that's where we have a sudden drop-off. Well, that cliff, at the bottom, we have some level surface. So it has a height of 23 meters. And actually, they give us 23.0 meters for an extra sig fig. And then we also know that it has an initial velocity of 15.0 meters per second at an angle of 20.0 degrees. So what that means is that if I'm launching a projectile from the top of the cliff, the horizontal line is kind of extending where it's sitting. So right now it's sitting at the top of the cliff. This is the horizontal. So to make an angle with the horizontal, imagine the rest of that line being extended and making an angle with that. So that angle was 20 degrees, 20.0. I'm just, since it's kind of small, it's not quite to scale, and that's okay if your drawings are not quite to scale. After that, they don't really give me much else. They give me the angle, they give me the initial velocity. Sorry, I can label that this initial velocity is 15.0 meters per second. So now what's going to happen is that this projectile is going to follow a parabolic trajectory or parabolic path, and it's going to end up landing on the ground. So the question says, find how far the projectile landed from the base of the cliff. Well, here's the base of the cliff. And so the distance that it landed from that is this area, which we know, since that's in the horizontal direction, that is delta x. So we're looking for delta x. So now I'm going to write down everything that we know and everything that we are assuming. In the x direction, we don't know delta x. So I'm going to leave that as a question mark. That's what I'm looking for. V initial. So I want to focus in on this V initial. This V initial is not V initial in the x direction. If you notice, it's on an angle, which means it has both x and y components. You need to make a triangle, and you can do it here, or you can make a larger triangle off to the side that will give you the components of your velocity. So on the hypotenuse, put your initial velocity, 15.0 meters per second. Put your angle in there, which was 20 degrees. And then at the base, we have V initial in the x direction and V initial in the y direction. Do not put any distances. So do not put the 23 on this vertical here. The reason why is because we're just using this triangle to find the components of velocity. So in other words, how fast is it moving forward and how fast is the object being projected up. We don't really care in this little miniature triangle about where the projectile is actually going. So now if Vix, if you notice, it's the adjacent side. So to find the adjacent side, we always use cosine. And so Vix, that's V initial in the x direction, is going to be 15 cosine 20. And if you type that into your calculator, and I should have written 20.0 for sig figs, but 15 cosine 20 is 14.0953, blah, 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 blah. To use 3 sig figs, that is 14.1 meters per second. Now, we also know that since the acceleration in the x direction, so I'm going to write this assumption, is 0 meters per second squared, that means that it's not speeding up or slowing down. So this 14.1 meters per second is also our v final in the x direction. So now let's focus on the y direction. we know that the cliff is 23 meters high, so that means that from where the projectile starts to where it ends up, it's going to drop 23 meters. Since it's going down, that means that our displacement in the y direction is going to be negative 23.0 meters. And going along with the other assumptions, v initial in the y direction, just like in the x, we're going to use that triangle. Since it is the opposite side of our angle, we're going to use sine. So this is 15.0 sine of 20. So typing that into your calculator, 15, and I did it again, leaving out that 0.0, but 15 sine of 20 is 5.13030215. 3 sig figs would give us 5.13 meters per second. Now, v initial in the y direction is not vf in the y direction because, for one, our projectile is going up in the beginning and it's going down at the end. So there's no way that those two are possibly the same. However, we do know that acceleration is negative 9.81 meters per second squared. And then we do not know delta t. So that's it for the assumptions. Now that we're done with assumptions, we can actually try to solve the problem. So if you remember your equations, we have 4 of them. These are displacement equals 1/2 vi plus vf delta t. We know that delta x is also 1/2 acceleration delta t squared plus v initial delta t. And then we also know vf squared is vi squared plus 2 acceleration displacement. And then v final is acceleration times time plus initial velocity. So we have 4 equations, and we need to solve for delta x. Now, when we look at these these equations, these delta x's are really either delta x or delta y, depending if we're looking at the horizontal or vertical direction. In addition, the vi and vf that you see in these equations are really either vix or vfx, or viy or vfy. It's not just the vi that's given to us. So in the x direction, because acceleration is 0, what ends up happening is that this term, this term, this term disappear. And really the only useful equation that we get, because of the fact that vi and vf are the same, we get that delta x is vi in the x direction, delta t. Well, if we try to plug in what we don't know delta x, that's what we're trying to find. vi in the x direction is 14.1 meters per second. And we don't know delta t. Well, what that means is our mission is now find delta t. But since we have no more equations in the x direction, we need to start looking in the y direction to figure out what delta t might be. So if you notice, we have in the y direction displacement, initial velocity, acceleration, and we're looking for delta t. That's 3 variables that we know and a 4th that we're looking for. So look for the equation that has all 4 of those, and the only equation that has that is this second one here. I know we've used it a lot. So write that equation, but instead of delta x, we're going to write delta y. So the equation is delta y equals 1/2 acceleration delta t squared plus v initial, but this v initial is in the y direction, so I'm going to write viy delta t. Now plug in everything you know. Delta y is negative 23. And just for space, I'm going to actually leave off the 0 on purpose this time. A is negative 9.81. If I multiply by 1/2, that is negative 4.905. And I'm okay with you using either 4.905 or 4.91 for sig figs. And v initial in the y direction was 5.13 delta t. So if you notice, this equation is a quadratic equation because we have a t that's squared and a t that's not squared. So we need to figure out how to solve this. And since I'm running out of space, I'm going to erase this line here so I can get more space. And I'm actually going to erase all of our formulas too, because I want to get the quadratic formula in here. Some of you forget that. So before we go any further, the quadratic formula applies for any function for which you have a variable squared plus a variable by itself plus a number. So here a, b, and c are numbers. They're called coefficients. To solve for x, x is going to be equal to negative b, so the opposite of whatever b is, plus or minus the square root of b squared. So I know I switched kind of from uppercase to lowercase, but don't mind that. Minus 4ac all over 2 times a. So now let's look at our equation and see what we can do. And this, ax squared plus bx plus c has to be equal to 0. So looking at the equation here, if you notice, we don't have everything equal to 0. So the very first thing we need to do is get this negative 23 out of here. So we have 0 equals blah, 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 blah. So I'm going to add 23 to both sides, and we get negative 4.905 delta t squared plus 5.13 delta t plus 23. So in order to move on, if you notice, and I'm going to get this in purple, this is my a value because it goes with the squared power. This is my b value because it goes with the single power. And this is my c value. So now plug in everything into the quadratic formula. And delta t is going to be negative b, so negative 5.13, plus or minus the square root of b squared, 5.13 squared, minus 4 times a, which is negative 4.905, times c, which was 23. And all of this is over 2 times a. Well, 2 times a, remember this a came from 1/2 times 9.81, so 2 times something that was 1/2, we're going to actually get right back to negative 9.81. So now all you have to do is evaluate this in your calculator. We're going to do this one step at a time. I usually like to focus on what's inside the square root first. So 5.13 squared minus 4 times negative 4.905 times 23. And you can literally type it in exactly how I just said that. So we're going to get negative 5.13 plus or minus the square root of 477.5769. Some of you may have jumped ahead and done the square root of that. So say you typed in square root of all that stuff. You actually end up getting, and if you didn't do that, you can do second square root, second answer to get 21.85. So if I take care of sig figs, that would be really 21.9. All over negative 9.81. So now comes a little bit of a tricky part. We have 2 possible answers. Notice the plus or minus. Evaluate both of those separately. Now that we know the quadratic formula, I don't really need that. So you're going to get negative 5 plus 21.9. And that ends up being, so either delta t is 16.77 over negative 9.81, or delta t equals negative 5.13 minus 21.9 divided by negative 9.81. So we get negative 27.03 over negative 9.81. And notice how one of them is negative and one of them is positive. Here we get 2.0 1.76 if I'm taking care of sig figs. And here, you end up getting 1.71. Sorry, that's negative 1.71. Because positive divided by negative is positive. So now, think about this. Change in time is negative or positive. I mean, in math, we had two solutions, but in physics, this one doesn't make sense. So we're going to throw out this answer, and we're just going to use this 2.76 seconds. So it takes 2.76 seconds for this projectile to go splat at the bottom of the cliff. Well, if we want to figure out delta x, we can go right back to this equation that had delta t in it, and all you have to do is multiply 14.1 times 2.76, and you end up getting 38.9 meters per second. Or sorry, not meters per second. I apologize. It is 38.9, but because this is a displacement, that is meters. So our final answer is 38.9 meters from the base of the cliff. So all I did was take this answer here and plug it in here for delta t, and you get your displacement. So on the quiz, or on the test in general, I could ask you an intermediate thing, such as how long did it take, and then how far did it go, or I could just ask you how far, and you would have to know I need to get delta t first. Regardless, though, if you get delta t and you struggle with getting delta x, or you show some partial understanding, then you'll get some partial credit. So I hope this helped. Make sure you know your quadratic formula and be able to use that.